This is chapter 4, linear estimation. This chapter will introduce some preliminary results to be used later for stochastic prediction, estimation, and control problems. The problem we will discuss can be formulated in this way. So let's consider two real stochastic processes, ST and NT. ST is a signal process and NT is a noise process. We want to observe or measure the signal, ST. Let's assume that the sum of ST and NT can be observed. So in other words, the signal is corrupted with the additive noise NT. Then YT are called the observations or measurements. The time index T, the capital T, can be either in continuous time or in discrete time. At time T, so let's assume T is a current time. We have obtained a realization of YT. So that is the observation. Let's call it. So we have obtained any Y tau. Tau from T0 and current time. The tau from T0 until the current time T. It can be either in continuous time and discrete time. It is often convenient to use the notation calligraphic YT to represent the available information. Like all the information available of Y tau from 0 to T can be represented by YT. So this is a collection of information until the current time T. So it's a T to indicate the current time. So the problem is use the observations YT to determine the best estimate of ST1. In continuous time process, the time index T is just a set of integers. Then the YT will be simply a vector. So the YT will be a vector. The YT0, the YT0, YT0 plus 1 until YT. In continuous time, this YT, it is a function defined on the interval. Say this is the T0, the current time T. It will be a function defined on this interval. This is the calligraphic YT. So the problem is, so based on this realization, YT, we will determine the best estimate of the value of the signal at the time T1. Depending on the time of T1, so the problem can be called smoothing problem, filtering problem, or prediction problem. If T1 is less than T, then the estimation problem, it is called a smoothing problem. If T1 is same with T, the estimation problem, it is called a filtering problem. If T1 is greater than T, then the estimation problem, it is called a prediction problem. The problem can also be formulated in slightly more general setting. So for example, we can formulate the problem as estimating a function of the signal st. It's not just the signal st itself, such as the derivative or integral from the observations of signal plus noise. Let's use y here to represent the space of the set of the observations which belong to the other yt's belong to the set of y, and all signals st belong to the set of s. Then the estimator is just a function which maps from y to s. So in general, the estimation problem is a challenge problem because we want to find the best function from infinitely many functions. So this function is called an estimator. For smoothing problem, it is also called interpolation problem. So therefore, the estimator is also called interpolator. For filtering problems, the estimator is called a filter. For prediction problems, the estimator, it is also called a predictor. Suppose we have this function, it's called f, function f maps from y to s. Once we have a realization, so that is the yt, then fyt will give us a value. Then this value is called an estimate. So let's use height s to represent the estimate of the signal s at time t1. To describe any of this problem, the smoothing problem, the filtering problem, or prediction problems, we must specify three things. First, we must specify the signal and noise processes. We must specify ST and NT. They can be either continuous time process or discrete time processes. Apart from the distinction of continuous time and discrete time, the process can be characterized by covariance function in the time domain or spectral density functions in the frequency domain. These two processes can also be modeled as the output of difference equations in a discrete time or the output of a differential equation in a continuous time with white noise inputs. Next, we must specify the criterion which define the best estimate. So there are also many possibilities to define the best estimate, to define the criterion. So for example, we can define the loss function. Let's call it J. The J is a function. The J is function. Then we must specify with some properties about this function. This is a real function. So let's assume so J is non-negative. So J is symmetric. And J is non-decreasing for positive x. So its shape will be something like this. all this. Then the loss function, so J S minus S hat. So S minus S hat is estimation error, the difference between the signal and its estimate. So the function itself is a random variable. Then the best estimate, X hat S, is the one which minimizes the average loss, the expectation of the function J S minus X hat. So if the X hat is same with S, okay, this function will be reach the minimum. There are, of course, also other ways to define the best estimate. The estimator was previously defined as a function which maps from Y to S. Last, we must specify the restrictions on the admissible estimators. For example, the function can be required. Okay, the function is a function which maps from Y to S. The function can be required to be linear or have other special properties.